Here is a number that should keep you awake at night. 2 trillion. That is the number of galaxies in the observable universe alone. Hundreds of billions of stars in our Milky Way galaxy alone. Around those stars, planets so countless they outnumber every grain of sand on Earth. Billions of those planets sit at exactly the right distance for liquid water, warmth and chemistry, capable of producing life. And our galaxy is just one of 2 trillion. The math screams that we should not be alone. Intelligence should have emerged countless times across 13.8 billion years of cosmic history. Civilizations should have left fingerprints across the stars, radio waves, megastructures, something. Yet, every instrument humanity has ever pointed at the sky has come back with the same haunting result. Absolute silence. Tonight, you will understand why that silence doesn't just puzzle astronomers, it genuinely terrifies them. Before we dive in, if you love exploring these kinds of deep space videos, a simple like or subscribe really helps this channel reach more curious minds like yours. Now, let everything soften, and together we drift into space. Something is wrong with the universe. Not wrong the way a machine breaks or a plan fails. Wrong the way a room goes quiet the moment you walk in. That particular kind of silence that tells you something was happening before you arrived, and whatever it was, it stopped. We have been listening to the cosmos for decades now, scanning, searching, pointing the most sensitive instruments humanity has ever built at thousands of stars, hundreds of thousands of stars. And the universe, vast, ancient, unimaginably populated by every calculation we know how to make, has sent nothing back. That is where this story begins, not with the silence itself, but with why it should not exist at all. To feel why that silence is so deeply strange, you first have to feel how large and full this universe really is. The observable universe, the portion of the cosmos we can actually detect and measure, contains roughly 2 trillion galaxies. Astronomer Christopher Consolis and his team at the University of Nottingham confirmed this in 2016, combining decades of Hubble Space Telescope deep field images with mathematical modelling to arrive at that number. 2 trillion galaxies. That figure does nothing until we make it real. If you counted 1 galaxy per second, never sleeping, never stopping, not pausing for a single breath, it would take approximately 63,000 years to finish. The Roman Empire was at its peak roughly 2,000 years ago. Agriculture was first invented around 10,000 years ago. 63,000 years ago, anatomically modern humans had not yet set foot in Europe. Neanderthals were the only humans who had ever walked those lands. That is how long it would take just to count the galaxies. Not the stars inside them, not the planets circling those stars. And each of those 2 trillion galaxies holds hundreds of billions of stars. Our own galaxy, the Milky Way, holds somewhere between 100 billion and 400 billion stars, spread across a flattened disk, roughly 100,000 light-years wide. And for most of human history, we had no way of knowing whether any of those stars had planets. We suspected, we hoped, but we did not know. Then, in March of 2009, NASA launched a spacecraft called the Kepler Space Telescope. Kepler had a single, carefully focused task: stare at one fixed region of sky and watch, with extraordinary precision, for the faint and almost imperceptible dimming that occurs when a planet passes in front of its star. Scientists call this a transit. Picture a moth crossing a lit street lamp on a dark night. Barely visible, almost negligible, but unmistakable if you are paying close enough attention. For 9 years, Kepler paid close attention, and what it found shattered every conservative estimate. Scientists had assumed planets might be fairly common. After Kepler, the word common no longer came close to capturing the truth. Our galaxy alone contains at least 50 billion planets, probably far more. 9 years of observations revealed something that would have seemed extraordinary just a generation ago. There are more planets in the Milky Way than there are stars. Planets are not the exception. Planets are the default. Among those billions, a 2020 NASA study drawing on Kepler's full dataset determined that the Milky Way holds at least 300 million potentially habitable worlds. 300 million planets where liquid water could exist on the surface, where the temperature is neither too scorching nor too frozen, where the basic chemistry of life, the same chemistry that produced every living thing you have ever seen or touched, could, in principle, do what it did here on Earth. 300 million in our galaxy alone, and there are 2 trillion galaxies. Take a moment with that phrase, potentially habitable, because it is easy to say and hard to absorb. Every star emits energy. The planets orbiting that star receive different amounts of that energy, depending on how close or far they sit. Too close, and the heat evaporates all surface water, leaving a scorched, barren world. Too far, and water freezes permanently, locking any potential chemistry beneath ice indefinitely. But in between, at just the right orbital distance, calibrated precisely to each star's particular brightness, liquid water can persist on a planet's surface. That band of possibility has a name, the habitable zone. Some astronomers call it simply the Goldilocks zone. Not too hot, not too cold, just right. In 2013, a research team at the University of California, Berkeley, and the University of Hawaii published a landmark analysis of Kepler data. They found that approximately 22% of Sun-like stars harbour an Earth-sized planet within their habitable zone. With roughly 100 billion Sun-like stars in the Milky Way, that single statistic implies approximately 20 billion habitable planets around Sun-like stars in our galaxy alone. And that does not include the hundreds of billions of smaller, cooler stars, many of which also carry worlds within their temperate bands. 20 billion in our one galaxy, on one quiet corner of a cosmos with 2 trillion of them. The universe does not look like a place that makes life rarely. The universe looks like a place that was built to make it. But here is the observation that truly transforms the picture. We have exactly one confirmed example of life, Earth. And the story of how quickly life arrived here carries implications that ripple through everything. Our planet coalesced from gas and dust roughly 4.5 billion years ago. For its first few 100 million years, Earth was barely survivable. A half-molten, asteroid-battered world subjected to a period scientists call the Late Heavy Bombardment, when the inner solar system was still dense with debris raining down from all directions. The surface was too violent, too unstable, too hostile for any sustained chemistry. And then, almost immediately after that violence subsided and the first stable oceans formed, life appeared. The oldest confirmed fossil evidence, stromatolites, the preserved remains of layered microbial communities, dates to approximately 3.5 billion years ago, found in ancient rock formations in Western Australia. Chemical traces suggest biological activity may reach back to 3.7 or even 3.8 billion years ago. Some carbon isotope signatures found in 4 billion-year-old zircon crystals from the Jack Hills of Australia hint at even earlier life, though that evidence remains scientifically contested. But even the most conservative reading tells us something profound. Earth formed 4.5 billion years ago. Life was present by 3.5 billion years ago, at most a billion years later, and likely much sooner. In cosmic terms, that is not a long wait. A billion years sounds vast until you hold it against the 4.5 billion year history of the planet itself, or the 13.8 billion year age of the universe. Life did not struggle against impossible odds for eons before finally arriving. On the first world we know of that could support it, life appeared almost the moment the conditions allowed. It is like a guest arriving the moment you open the front door. That observation is not a small detail. It is, potentially, everything. Because if life does not require billions of years of improbable chemistry to emerge, if it tends to appear quickly when given the right environment, Then in a galaxy holding 300 million potentially habitable worlds, the question stops being whether life arose elsewhere. The question becomes how many times and how long ago. In November of 1961, a young astronomer named Frank Drake arrived at the National Radio Astronomy Observatory in Green Bank, West Virginia, to organize the very first scientific conference dedicated to the search for extraterrestrial intelligence. The guest list was small but remarkable. Among the 10 attendees was a 27-year-old Carl Sagan, the youngest and, at the time, least famous person in the room. Drake needed an agenda. A few days before the meeting, he sat down and wrote what would become one of the most discussed equations in the history of science, not because it solved the problem, but because it gave the problem its shape. Drake listed every factor that would determine how many communicating civilizations existed in the Milky Way at that moment, how many new stars form each year. Of those, how many develop planets? Of those planets, how many are in habitable zones? Of those, how many actually produce life? Of those, how many eventually produce intelligent life? How many of those intelligent species develop the technology to broadcast signals into space? And, crucially, how long do those civilizations survive before going silent? Multiply those factors together and you get one number, an estimate of the civilizations in our galaxy currently sending signals we could, in principle, detect. On the morning of November 1st, 1961, Drake wrote the equation on a chalkboard while the guests sipped their coffee. From that moment, the search for life beyond Earth stopped being a philosophical question and became a scientific one. The equation is not a precise calculator. Drake never intended it to produce a fixed answer. What it does is reveal the exact shape of our ignorance. Most of its variables remain deeply uncertain. Scientists disagree on them, sometimes by factors of millions. A cautious reading of the equation produces a handful of civilizations. An optimistic one produces millions. But even the most conservative values, grounded in everything we now know about planets and the emergence of life on Earth, point to a galaxy where life has had enormous repeated opportunities to arise, evolve, and reach outward. At the end of that 1961 conference, as the attendees raised a glass of champagne, the observatory director offered a toast. To the value of L, he said, L being the lifespan of a technological civilization, may it prove to be a very large number. Step back now and hold the full picture in one frame. 2 trillion galaxies, hundreds of billions of stars in our galaxy alone. Planets so common they outnumber the stars themselves. 300 million worlds in potentially habitable zones, just in the Milky Way. Life appearing on Earth almost the moment conditions allowed. An equation that, even when populated with cautious estimates, describes a cosmos filled with opportunity. By every reasonable calculation, the universe should be teeming with intelligence. Not just simple, single-celled life, huddled near underwater vents. Complex life, old life, civilizations that arose billions of years before our sun was even born. Species that had time enough to spread, to build, to leave marks on their galaxies that a civilization like ours, with our radio telescopes and our mathematics, should be able to see from across interstellar distances. If even a tiny fraction of those 300 million habitable worlds in just our galaxy produced intelligent species, and if even a fraction of those species reach the technological stage, the sky above us should be alive with signals, transmissions, patterns, evidence. The cosmos should be loud. Scientists were confident it would be. They built the expectation step by careful step. The logic was sound. The numbers were real. The universe seemed to demand it. But here is the reality. No confirmed signal. Not one. Decades of listening. Thousands of stars surveyed. Millions of frequencies monitored. And only silence. No repeating transmission. No structured pattern that could not be explained by natural physics. no megastructures circling distant suns, no visits, no trace of anyone reaching back. The universe appears, against all expectation, to be profoundly quiet. Stand outside on a clear night and look up. Every point of light you can see is a star, most of them likely with planets, many of them with worlds in habitable zones. Some of those stars are older than our sun by billions of years, and not one of them, as far as we can tell, has ever sent us so much as a whisper. Picture a city at night, stretching to the horizon and beyond. If even one window in that city holds a burning light, you can see it from miles away. You don't need to search every room or knock on every door. The light finds you. Now imagine a city with hundreds of millions of buildings spread across billions of years of history, every window dark. That is what we are looking at when we look at the sky. We built this expectation carefully, honestly, from the ground up. The galaxies are real, the planets are real, the data from Kepler is real, the early appearance of life on Earth is real. The Drake equation is grounded in real science, crafted by real scientists who had every reason to believe it would eventually yield a large number and a full sky. And yet, silence. That silence has a name, and the man who first gave it one did not do so in a journal or a formal paper or a prepared lecture. He said it over lunch, a single offhand question that would echo through science for the next 70 years and has never, not once, been fully answered. His name was Enrico Fermi, and the question he asked was not in a paper, not in a laboratory, not in a formal presentation to his colleagues at the world's most advanced physics institution. He asked it over lunch. In the summer of 1950, Fermi, one of the architects of the atomic age, a Nobel Prize winner, the physicist who built the world's first controlled nuclear reactor, was walking toward the dining hall at Los Alamos National Laboratory in New Mexico. Around him were some of the most brilliant minds of the 20th century. The conversation that morning had drifted toward flying saucer reports, UFO sightings making headlines across America. The men laughed about it. They moved on to other things. They sat down. Food arrived. The conversation shifted entirely. And then, out of nowhere, Fermi blurted a question. His colleague Edward Teller would later remember that what followed was immediate, involuntary laughter. Not because the question was funny, but because everyone at the table understood instantly, without explanation, exactly what Fermi was asking. He had not explained himself. He had not built up to it. He had not mentioned planets or civilizations or radio telescopes. He simply said, "Where is everybody?" That question still has no answer. 75 years later, with instruments so sensitive they can detect the faint whisper of a galaxy 13 billion light-years away, with artificial intelligence scanning petabytes of data from telescopes on 6 continents, no confirmed answer. Not one verified signal, not one confirmed artifact, not one unambiguous response to what Fermi's quiet, offhand question was really asking. If the universe is as large and old and full of possibility as we know it to be, why haven't we heard from anyone? This is what became known as the Fermi paradox. And before we can understand why it matters so deeply, we need to feel the full weight of what makes it a paradox at all. Our galaxy, the Milky Way, is approximately 13.6 billion years old. According to NASA and research built on stellar archaeology from ESA's Gaia mission, the Milky Way began forming just a few 100 million years after the Big Bang itself. That makes it almost as old as the universe. Our solar system, the Sun, Earth, and every planet orbiting it is 4.5 billion years old. That means the Milky Way existed for more than 9 billion years before our world was born. 9 billion years is an almost unworkable number. Let us try to make it real. If the entire 13.6 billion year history of the Milky Way were compressed into a single calendar year, our sun would not ignite until the first day of September. Earth forms that same week. The first life on Earth, ancient microbial communities clinging to the floors of shallow primordial seas, arrives in the final days of September. The dinosaurs do not appear until Christmas Eve. They go extinct on December 29th. Every human being who has ever lived, every language ever spoken, every civilization from the first walled city to the present moment, all of recorded human history fits inside the final 12 seconds of New Year's Eve. 12 seconds. That is where we are in the story of this galaxy. And before our 12 seconds began, 9 billion years of cosmic opportunity had already passed. Now comes the part that makes the silence genuinely disturbing. Scientists began asking a specific question. Given enough time and even the most conservative assumptions about interstellar travel, how long would it take a spacefaring civilization to spread across the entire Milky Way? The galaxy, as we have seen, is 100,000 light-years wide. That is an incomprehensible distance at human scales. But civilizations that survive long enough develop technology. Technology advances, and the mathematics of expansion, the same mathematics that describes how populations spread, how invasive species colonize continents, how ideas propagate through a network, is merciless in what it predicts. Astronomer Michael Hart, writing in the Quarterly Journal of the Royal Astronomical Society in 1975, worked through the numbers carefully. He found that even if a civilization traveled at just 1/10 of the speed of light, a speed we have never come close to achieving, but also a speed that is physically plausible, far beneath the known limits of the universe, such a civilization could send probes or colony ships from star to star. Each destination becomes a new launch point. Each new world sends out its own expeditions. The wave of expansion fans outward like a forest fire spreading from tree to tree. At 1/10 the speed of light, Hart calculated, the entire Milky Way could be traversed in under 1 million years. 1 million years sounds like a long time. But remember the calendar. On our compressed year, 1 million years is roughly 39 minutes. In the 9 billion years before Earth even formed, a civilization with modest interstellar technology could have crossed the galaxy, not once, but 9,000 times over. More recent modelling supports this. Computer simulations by researchers including astrophysicist Jason Wright at Penn State, published in 2019, demonstrate that even with slow spacecraft and long delays between launches, the Milky Way can become substantially settled within a time frame far shorter than its age. The math does not require warp drives or science fiction. It requires only persistence and time in this galaxy has been available in extraordinary abundance. The silence gets harder to explain with every calculation we do. Here is where the Fermi paradox expands beyond what most people realize when they first hear it. It is not simply about visits. It is not simply the question of whether an alien spacecraft has landed. That is actually the most demanding version of the question, the one most easily dismissed with arguments about distance, fuel, and motivation. The paradox has 3 distinct layers, each harder to explain away than the last. The first layer, no visits, no confirmed evidence that any extraterrestrial civilization has ever been present on Earth, or anywhere in our solar system. The second layer, no signals. We have been listening for radio transmissions from the cosmos since 1960, 65 years of scanning the sky at frequencies chosen specifically because they are physically universal, because any civilization capable of technology would likely recognize them. No confirmed transmission, not one. The third layer, no megastructures. A sufficiently advanced civilization, the kind that has existed for millions or billions of years, should be building on a scale detectable from across the galaxy. Structures around stars to capture their energy, patterns in starlight that betray the presence of vast engineering. Nothing has been confirmed. No visits, no signals, no structures. All 3 simultaneously absent across a galaxy 13.6 billion years old, with at least 300 million potentially habitable worlds in it. Scientists gave this triple absence a name. They called it the Great Silence, And the silence is not merely the absence of noise, it is the presence of a question that every observation deepens and no data has yet resolved. A word here about the word paradox, because it matters. In everyday conversation, paradox often means something strange, or contradictory, or philosophically confusing. But in science, a paradox means something more specific. Two sets of evidence that both appear valid, point in opposite directions, and cannot be simultaneously true. On one side of the Fermi paradox, everything we know about the size, age, and habitability of the galaxy says the cosmos should be full of intelligence. The math is clear, the observations are real, life appeared quickly on Earth. Planets capable of supporting life are common. The galaxy is ancient. By every reasonable estimate, civilizations should have arisen long ago, spread widely, and left unmistakable signs of their existence. On the other side, complete silence. No confirmed contact, no signal, no artifact. Both sides are grounded in real data. That is what makes this not merely a mystery, but a paradox. And paradoxes in science are not curiosities. They are doors. They always lead somewhere. We have not simply sat quietly and wondered. We have listened. The organized search for extraterrestrial signals began in 1960, when Frank Drake pointed an 85-foot radio telescope at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened for structured transmissions at the frequency of neutral hydrogen. That search, called Project Ozma, heard nothing, but it was a beginning. Since then, the search has expanded enormously. Programs have scanned hundreds of thousands of stars across multiple frequencies using telescopes, on multiple continents, processing data with algorithms and, more recently, artificial intelligence systems capable of filtering through volumes of information no human team could manage. Breakthrough Listen, launched in 2015 with $100 million in funding and access to some of the most powerful radio telescopes on Earth, currently surveys 1 million nearby stars and 100 nearby galaxies simultaneously. The technology we are using now would have seemed miraculous to Frank Drake in 1960, and in all of that time, across all of those stars, with all of that technology, only one observation has ever made scientists reach for a pen and write the word that gave it its name. Sit for a moment in a quiet office in Delaware, Ohio. The year is 1977. A volunteer astronomer named Jerry Amon is doing what he does most evenings, sifting through computer printouts from Ohio State University's Big Ear Radio Telescope, scanning rows of numbers that represent the intensity of radio signals arriving from deep space. The work is methodical, repetitive, mostly unrewarding. Amon has done this hundreds of times and found nothing unusual. On August 15th, the Big Ear swept across a region of sky near the constellation Sagittarius. The telescope recorded the data. A few days later, Amon sat down with the printout, and then he stopped. One sequence of numbers stood out from everything around it, a sharp, rising, then falling pattern of signal intensity, precisely 72 seconds long, exactly at the frequency scientists had long predicted an extraterrestrial signal would use, the frequency of neutral hydrogen, the most abundant element in the universe. The signal arrived from deep space, not from Earth. It had a narrowband structure, a signal so focused it suggested it came from a single direction, not scattered noise. Its behavior matched almost perfectly what the Big Ear's beam pattern would produce if it swept past a point source transmitting from the cosmos. Amon circled the numbers in red ink, and next to them, in the margin, he wrote one word: wow. The wow signal remains, nearly 50 years later, the strongest candidate for an extraterrestrial radio transmission ever detected. Researchers used dozens of telescopes to search for it again. More sensitive instruments, more hours of observation time, scanning the same region of sky again and again. The signal never repeated. No natural explanation has been confirmed. No artificial source has been identified. What it was, no one still knows with certainty. Eamon himself said in 1994, "We should have seen it again when we looked for it 50 times. We did not. The wow signal is what the Fermi paradox sounds like in the data. A single blip, 72 seconds, never repeated. Strong enough to make a careful, experienced scientist reach for a red pen. And then, nothing. For decades, it stood as a tantalizing possibility that something, somewhere, had briefly announced itself. But a signal that arrives once and disappears explains nothing about the broader silence. If anything, it makes the silence louder. Because here is the question the wow signal forces into focus. If one such signal could appear even briefly, even once, even unconfirmed, then across a galaxy of hundreds of billions of stars, over billions of years, where are the rest of them? Something is filtering them out. Something is holding the universe back from the fullness that every calculation says it should have. Some force, some barrier, some explanation that we have not yet looked in the face, standing between the universe's apparent potential and the silence we actually observe. Scientists gave that barrier a name too, and it may be the most unsettling idea in the entire history of the search. The barrier has a name. An economist named Robin Hanson gave it that name in 1996 in a quiet academic essay that most people outside the fields of astrobiology and existential risk had never heard of. He was not trying to be dramatic, he was trying to be precise, and the precision of what he wrote is exactly what makes it so difficult to set aside. Hanson looked at the same evidence we have been examining: the age of the galaxy, the abundance of habitable planets, the speed at which life appeared on Earth, the colonization timescales, the total and unbroken silence. And he drew a conclusion that was not speculative, not philosophical, not a matter of opinion. It was a logical necessity. Something, somewhere in the sequence from dead chemistry to spacefaring civilization, must be extraordinarily unlikely. He called it the Great Filter. The name sounds like a mechanism, a device, something that consciously sorts civilizations the way a net sorts fish from water. But that is not what it is. The Great Filter is not a thing, it is a deduction. Think of it this way. Imagine you are handed a list of 100 lottery tickets and told that at least 99 of them are losers. You do not need to inspect each ticket to know the odds are stacked. You know that, almost certainly, almost all of them fail. The Great Filter is that knowledge applied to the emergence of intelligent life. If the universe is as old and full of opportunity as we know it to be, and yet the galaxy appears completely empty of advanced civilizations, then something on the path from the beginning of life to the stars is stopping nearly everything from getting through. Not occasionally, not usually, almost always. The filter is the name for wherever that stopping happens. And here is the question that has haunted every scientist who has seriously engaged with this idea. Where, exactly on that path, does the stopping occur? Because the answer to that question does not merely describe the history of other civilizations in the galaxy, it describes our future. Hanson mapped out the path. Not arbitrarily, he drew on biology, chemistry, astronomy, and the history of life on Earth to construct a sequence of steps that any civilization in the universe would need to traverse in order before it could become the kind of civilization we would be able to detect. The path begins before life even exists. A planet needs a star of the right kind, stable, long-lived, not too variable, not too violent in its radiation. The star needs to have formed with the right chemical ingredients: carbon, oxygen, hydrogen, nitrogen, present in sufficient amounts. The planet itself needs to sit in the right orbital band, with the right composition, the right size, the right geological activity, the right conditions to hold liquid water on its surface across geological timescales. Already, on this first step alone, the requirements are significant. But assume all of that is met. Life still does not appear automatically. The chemistry of life, the spontaneous organization of inorganic molecules into self-replicating structures, needs to happen. Exactly how this occurs on Earth is still not fully understood. Scientists know that it happened. They know it happened relatively quickly, but the precise mechanism remains one of the deepest unsolved problems in all of science. Whether it is common or extraordinarily rare is genuinely unknown. Assume again that life begins. Now comes one of the most important steps, and one of the strongest candidates for where the filter might sit. For the first 3.5 billion years of life on Earth, almost nothing happened. That sentence deserves to sit for a moment. Life appeared quickly after the oceans formed, but what appeared was simple, microscopic. Single-celled bacteria and archaea, prokaryotes, cells without a nucleus, without internal compartments, without the complex internal machinery that allows cells to become specialized, to cooperate, to build bodies. These organisms were extraordinarily successful. They colonized every corner of the planet. They transformed the chemistry of the atmosphere. They are still here today, thriving in every environment on Earth, from ocean hydrothermal vents to Antarctic ice. But they never got more complex on their own. For more than 1.5 billion years, life on Earth stalled at the level of single-celled simplicity. And then, roughly 2 billion years ago, something happened that may never have happened before in the history of the universe, and has only happened once in the 4.5 billion year history of this planet. One ancient bacterium was absorbed by another cell, and instead of being digested, it survived. It became a permanent resident, a symbiont. Over generations, the engulfed bacterium lost its independence entirely and became an organelle, an internal power source, inside its host. That merger produced the eukaryotic cell, a cell with a nucleus, with internal compartments, with the ability to process energy at a level of efficiency that simple bacteria never achieved. Every animal, every plant, every fungus, every organism with more than one cell that has ever existed on Earth descends from that single moment of cellular merger. Biochemist Nick Lane at University College London has written that the eukaryotic cell was a genuinely improbable event, a hopeful monster born in an unlikely merger 2 billion years ago. In the entire recorded history of life on this planet, that specific endosymbiotic event, one cell permanently absorbing another and both surviving to become something new, appears to have happened exactly once, one time, in 4.5 billion years. That is the kind of number that makes scientists pause, but the eukaryotic cell was only one step on the ladder. What came after it required further improbabilities, stacked on top of each other. Eukaryotic cells eventually had to become multicellular, to stop living as isolated individuals and begin organizing into coordinated bodies. That transition also appears in the fossil record as a relatively rare and difficult crossing. Then multicellular life had to develop specialized tissues, nerve cells, muscle cells, sensory organs, then complex nervous systems, then brains sophisticated enough to model the world, plan ahead, use tools, communicate, cooperate across generations, and accumulate knowledge. Then, and this is a step no other species on Earth has completed, one lineage had to develop technology, the ability to harness energy beyond its own body, fire, agriculture, industry, and eventually the capacity to reach into space. Each of these transitions is individually remarkable. Each is a crossing from one level of complexity to a fundamentally higher one. And across the entire observed history of life on Earth, every single crossing was rare, slow, and often took hundreds of millions of years to occur. The Great Filter does not require any single step to be impossible. It only requires that across a long enough chain of genuinely unlikely transitions, the probability of completing all of them drops towards something vanishingly small. Multiply enough improbable steps together, and even in a galaxy with hundreds of billions of planets, the result is silence. Here is where the great filter divides into two possibilities, and the difference between them is not academic. For us, personally, here, now, the difference between these two possibilities may be the most consequential distinction in the history of human thought. The first possibility, the filter, is behind us. This means the bottleneck, the hardest, rarest, most improbable step already happened in Earth's past. Perhaps life itself is extraordinarily rare. Perhaps the eukaryotic cell merger was so unlikely that it only happened once across the entire observable universe. Perhaps multicellular complexity crossed a threshold so narrow that virtually nothing else in the cosmos has managed it. If any of this is true, then the silence makes sense. Earth is not just one habitable planet among many. Earth is a profound exception, perhaps the most remarkable accident in 13.8 billion years of cosmic history. We would be alone, not because the universe failed to provide opportunity, but because we are the one place where something extraordinarily improbable kept happening over and over. If the filter is behind us, the silence is explained, and humanity's future, while still uncertain and full of its own challenges, is not predetermined toward failure. The second possibility is the one that gives serious scientists sleepless nights. The filter is ahead of us. This would mean the steps we have already passed, the formation of life, the eukaryotic cell, multicellular bodies, intelligent brains, are actually not that unusual. Many civilizations across the galaxy have navigated them. Many species have reached roughly where we are. Perhaps some reached much further. But all of them, or nearly all of them, hit something after our current stage that stopped them. Something that almost no technological civilization survives. Something that awaits us too. What that something might be, the great filter does not specify. A civilization capable of splitting the atom is also capable of poisoning its own atmosphere. A civilization advanced enough to engineer biology is also capable of releasing something it cannot control. The same intelligence that builds radio telescopes can also build weapons of incomprehensible destructive power. And perhaps, across all the civilizations that have ever arisen in this galaxy, the technological crossroads we are now approaching has a track record we cannot see, but whose result we can infer from the silence. This is the place where some people will want to push back. The great filter sounds like pessimism dressed in mathematics, like an excuse to be gloomy about human prospects. But here is what philosopher Nick Bostrom at Oxford University pointed out in a careful, widely read essay published in 2008. One of the most important paragraphs in modern scientific thinking about our future. The great filter, he wrote, is not pessimism. It is a deduction from evidence, and the silence is the evidence. The universe has had 13.8 billion years to produce spacefaring civilizations. The Milky Way has had 13.6 billion years. The math of colonization says a single civilization with modest technology could have crossed the galaxy thousands of times before Earth even formed, and the galaxy shows no sign of that. Not a signal, not a structure, not a trace. Something is ending almost every story before it gets to that stage. The only question is whether our story has already passed the ending, or whether it lies somewhere ahead. Bostrom added one more element to this reasoning that feels genuinely strange the first time you hear it. He argued that of all the discoveries humanity could make in its exploration of the solar system, one of the most emotionally exciting would also be one of the most scientifically alarming. If our space missions to Mars, or Europa, or Enceladus were to find clear evidence of independently evolved life, even simple microbial life with no connection to Earth, most people would celebrate. Headlines would call it the greatest discovery in human history, and in one sense it would be. But in terms of what it implies for the great filter, it would be, in Bostrom's precise words, very bad news. Because finding life independently evolved elsewhere in our own solar system would mean that abiogenesis, the emergence of life from chemistry, is not rare at all. Life gets started easily, which means the great filter is almost certainly not in the distant past of biology, which means it is almost certainly still ahead of us. The emptier and more barren our solar system turns out to be, the better it is for our long-term prospects. The more lifeless our cosmic neighbourhood appears, the more likely it is that the hardest crossing is one we have already made. We are, in the strangest possible reversal of ordinary hope, rooting for emptiness. The great filter does not tell us where the barrier sits. That is both its power and its limitation. It is a logical framework, not a prediction. It tells us only that the barrier exists somewhere, and that the silence of the galaxy is its evidence. But among the candidates for where it might be hiding, one class of hypothesis stands apart from the others, not because it is the darkest possibility, but because it has the most sophisticated scientific reasoning behind it. Not a catastrophe imposed from outside, not a cosmic accident, something subtler. Something that would explain not just why civilizations fail to expand, but why they might choose not to, or why they might not need to. And understanding that requires us to think about what an advanced civilization might actually want, and whether any of those desires would ever make them visible to something as young and as loud and as brief as us. What if the universe is not empty? What if the silence we have been trying to explain is not the absence of intelligence, but intelligence's most sophisticated response to its own situation? What if, scattered across this galaxy, there are minds that know we are here, that have done the calculations, that have looked outward at the same dark sky we look at, and made a deliberate choice to say nothing? These are not comfortable ideas, but they are scientifically serious ones, and they force us to reconsider something we have quietly assumed from the beginning of this search, that any civilization capable of communicating across the stars would want to. From the moment Frank Drake pointed his radio telescope at two nearby stars in 1960, the entire architecture of the search for extraterrestrial intelligence has rested on a single unexamined premise. We assumed that if intelligence is out there, it broadcasts. We assumed that the desire to reach outward, to announce existence, to make contact, is a universal feature of any mind advanced enough to build a transmitter. But that assumption comes entirely from us, from our culture, our moment in history, our particular blend of curiosity and optimism about the cosmos. And the universe has no obligation to share our values. In 2008, Chinese author and engineer Liu Cixin published a science fiction novel called The Dark Forest. It became, within years, one of the most discussed books in the world, not because it was fiction, but because scientists and researchers at SETI institutions found themselves unable to dismiss the hypothesis it named. The idea Liu articulated is this: the universe may be full of civilizations, but any civilization that survives long enough becomes sophisticated enough to understand one terrifying reality, that revealing your location is existentially dangerous. Think about what this means. Two civilizations meet across the void of space. Neither can know the other's true intentions. Neither can fully verify the other's honesty. Technology advances unpredictably. A civilization that seems primitive today may develop weapons tomorrow that did not exist yesterday, and across interstellar distances there is no time to wait and learn. A signal from an unknown source takes years to arrive. A response takes years more. By the time trust could be built, if trust were even possible, circumstances may have shifted in ways neither side can predict. In a situation of perfect, irreducible uncertainty, where the cost of being wrong is extinction, the rational calculation, Liu argued, is to eliminate the unknown before it eliminates you. Picture the darkest forest at night. Every tree casts shadow. Every shadow could conceal something. You have no way to see what is watching. In that forest, the animal that makes noise gets found. The animal that survives is the one that moves without a sound, that leaves no trail, that gives nothing away. If that is the logic governing intelligence in this galaxy, then every civilization that learned it would go silent, and the universe would look exactly as it does right now. And yet, scientists push back hard. The most significant objection is this: for the dark forest to explain the silence completely, every civilization in the galaxy would need to independently arrive at exactly the same conclusion. Not most, not the majority, every single one. Because if even one species, anywhere in the galaxy across billions of years of history, decided that the risk was worth taking, or had a different psychology, or made a different calculation, we would likely see some evidence of it. A signal, a megastructure, a pattern. The hypothesis requires perfect, universal, galaxy-wide consensus on a strategic decision. And on Earth, where cooperation failures are among the most documented features of intelligent behavior, scientists find it hard to believe that every alien mind would arrive at identical conclusions. Planetary scientist and astrobiologist Ian Crawford at Birkbeck University, London, notes that it is difficult to explain why all civilizations would adopt the same fear-based strategy. So the dark forest is a serious hypothesis, but not a settled one. And the silence may have explanations that do not require predators at all. Here is a problem that cuts differently and more quietly. We have been searching for radio waves. That is what our telescopes are designed to detect. Radio waves are what we use, so we assumed radio waves are what others use. But radio transmissions are not a permanent feature of an advanced civilization. They are a phase, a brief, early stage of development that a technological species passes through on its way to something else. Think about our own trajectory. We started broadcasting radio waves widely at the turn of the 20th century, but by the late 20th century we were already moving away from open broadcast, towards satellite transmission, fiber optic cables, and digital communication systems that leak far less signal into space. A sufficiently advanced civilization, even one broadcasting actively, might become progressively less visible to a radio telescope simply by becoming more efficient with its communication technology. Researchers at the Search for Extraterrestrial Intelligence have noted this explicitly, as SETI scientists at Arizona State University argued in a 2025 paper. The traditional search has been an anthropocentric one, looking for signals that resemble what we currently produce during the specific technological phase we currently occupy. A civilization 1,000 years ahead of us might communicate using focused laser pulses, or neutrino beams, or quantum entanglement-based systems, operating in ways we have not yet conceived. We would not detect any of those with the instruments we currently use. We could be listening at entirely the wrong frequency, in the wrong medium, looking for the wrong kind of signal. Not because the universe is silent, but because we are searching with the equivalent of a candle held up to the dark, wondering why it does not illuminate the stars. In 1973, a Harvard astrophysicist and researcher at MIT's Haystack Observatory named John Ball published a paper proposing what became known as the zoo hypothesis, and of all the ideas we are considering, this one carries perhaps the strangest combination of comfort and unease. Ball's argument was this: advanced civilizations may know we exist. They may have been watching us for centuries, or longer, and they may have made a deliberate collective decision not to interfere. Not because we are a threat, not because they are afraid, but because we are, in some sense, a protected place. The way we set aside wildlife preserves not to exploit them, but to let them develop on their own terms. The way a careful naturalist observes without disturbing. Ball described it as a one-way mirror. They can observe us. We cannot observe them. This idea has a parallel that most people will recognize. In the Star Trek universe, it was formalized as the Prime Directive, the rule forbidding contact with civilizations that have not yet reached a certain technological threshold. Ball was proposing that something like that principle might be real, not as science fiction, as galactic policy. The zoo hypothesis has its own serious objections. The most pointed one is simply this: it requires that every advanced civilization in the galaxy agree to maintain this non-interference policy perfectly for millions of years, with no defectors, no dissenters, no rogue faction deciding to break the silence. On Earth, we have never once managed to maintain any global policy without someone eventually defecting from it. And scientists note that the hypothesis may tell us more about our desire to be significant, to believe that we matter enough for others to protect us, than about the actual structure of the cosmos. But the zoo hypothesis remains a genuine, documented scientific proposal, and it cannot be ruled out. Set aside fear and strategy and choice. There is one explanation for the silence that requires none of them, and it is written into the laws of physics themselves. The nearest star to our own sun is Proxima Centauri. It sits 4.2 light-years away. That means any signal we send there, travelling at the speed of light, the maximum speed permitted by the known universe, takes 4 years and 2 months to arrive. A response takes another 4 years and 2 months to return. A single exchange of messages with our nearest stellar neighbour takes more than 8 years, not due to any failure of technology, not due to any lack of effort, simply because of the size of the gap between us. Now hold that against the Milky Way, 100,000 light-years wide. A signal from one side takes 100,000 years to reach the other, even if a civilization on the far side of our galaxy knew we were here and replied the moment they detected us. Their response would arrive when the entire recorded history of humanity would have repeated itself many hundreds of times over. The galaxy is not just large in space, it is large in time, and that temporal gap creates a different kind of invisibility. Picture two fires burning in a vast dark plain. If they burn simultaneously, each is visible to the other. But if they are separated by enough time, if one burns, dies, and the plain falls dark for 10,000 years before the second fire ignites, then neither sees the other. Not because the fires were hidden, simply because they never overlapped. Our civilization has been transmitting recognizable signals into space for just over 100 years. 100 years out of a galaxy 13.6 billion years old. That is less than 1/millionth of 1% of cosmic time. The window during which we have been detectable from across the stars is, on any cosmic scale, effectively instantaneous. If another civilization had been transmitting for 1,000 years and went silent 500 years ago, their last signals are still travelling outward at the speed of light and will not reach us for centuries or millennia more, depending on their distance. If they transmit again 10,000 years from now, we will have come and gone before that signal arrives. Two ships passing in the dark of the same ocean but separated by centuries. Neither sees the other. Neither knows the other existed. The ocean is not empty. The timing is simply not aligned. Feel the weight of your own breath for a moment. You are here, right now, in a specific point in time that took 4.5 billion years to produce. You exist in one of the most vanishingly brief slivers of cosmic history imaginable, and the civilizations that may have filled this galaxy, if they existed, may have lived and died in their own slivers, separated from ours by gulfs of time that no signal and no telescope and no amount of listening could ever bridge. The silence may not be a wall, it may simply be the shape of time itself. Between the dark forest and the zoo, between technological invisibility and temporal mismatch, between fear and physics, we have assembled a collection of reasons why intelligence, even abundant intelligence, might not leave the kind of marks we have been looking for. But each of these explanations shares a weakness. Each requires us to assume something about how advanced civilizations behave, and we have no examples to draw from except ourselves. What we have not yet done is look at what the universe itself might be trying to tell us. Not through the absence of signals, but through the behavior of stars and the structure of light. Because there are objects in this galaxy that behaved in ways no natural process could explain easily. Objects that made scientists sit up and reach for extraordinary hypotheses, and the search for those physical signatures, the search for what an advanced civilization would actually build, leads somewhere that neither radio silence nor game theory can fully address. Every explanation we have explored so far has shared one hidden assumption. The dark forest assumes civilizations are afraid. The zoo assumes they are protective. The timing mismatch assumes they existed but missed us. All of these are behavioral explanations. They describe choices or misfortunes or the cruel arithmetic of distance and time. But what if the problem runs deeper than behavior? What if the universe is simply not the kind of place we assumed it was? There is a second category of explanations for the Great Silence, not about what civilizations do or choose or fear, about what the universe is, about whether the conditions we assumed were widespread are actually vanishingly rare, about whether what we observe when we look at the sky reflects what is truly out there. These explanations do not require any alien psychology. They do not require any conspiracy or any choice. They rest entirely on the structure of reality itself, and the first of them begins with Earth. In the year 2000, two scientists at the University of Washington published a book that landed like a cold contradiction to everything Carl Sagan had spent decades arguing. Paleontologist Peter Ward and astronomer Donald Brownlee called their book simply Rare Earth. Its argument was careful, methodical, and deeply unsettling. We had assumed, since the Copernican revolution, that Earth is not special, that it is a typical rocky planet, orbiting a typical star in a typical galaxy. Frank Drake and Carl Sagan had built their most optimistic estimates on exactly that assumption, that the universe is full of places like ours, and so full of life like ours. Ward and Brownlee looked at the geology and the astronomy and concluded, we were wrong. Not about microbial life. Simple life, bacteria, archaea, single-celled organisms, may well be common, but complex life, the kind that requires stable conditions across hundreds of millions of years, the kind that eventually produces nervous systems and brains and technology, that is something different entirely. Consider what Earth actually requires. Not just liquid water and the right temperature, though those matter enormously. Consider the full inventory of what had to be in place for complex life to emerge here. A star stable enough to not vary dramatically in energy output across billions of years. A planet of roughly the right mass, large enough to hold a thick atmosphere, but not so large that it becomes a gas giant. A giant outer neighbour like Jupiter, sitting at just the right orbital distance to act as a gravitational shield, deflecting incoming comets and asteroids before they can strike the inner solar system. Without Jupiter, Ward and Brownlee argued, the rate of catastrophic impacts on Earth would likely be so high that complex life would be repeatedly wiped out before it could develop beyond the simplest stages. Then there is the Moon. Earth's moon is enormous relative to our planet, larger by proportion to its parent body than any other moon in the solar system around a rocky planet. And that size matters in a way most people have never considered. Our moon acts as a gravitational anchor for Earth's axial tilt, the angle at which our planet leans as it orbits the sun. Without the moon's stabilizing influence, that tilt would wander chaotically over geological timescales, shifting from nearly upright to nearly sideways and back again. Seasons would not merely be uncomfortable, they would be catastrophic, ice ages and sweltering heat alternating in cycles too rapid and too extreme for complex ecosystems to adapt. The stable, moderate climate range that allowed animal life to evolve on Earth across hundreds of millions of years depends, at least in part, on the moon holding our tilt in place. And how did we get such an unusually large moon? by an accident so improbable that scientists still marvel at it. Roughly 4.5 billion years ago, a body roughly the size of Mars, a protoplanet scientist called Theia, struck the young Earth at precisely the right angle and velocity to eject an enormous amount of material into orbit, which then coalesced into our Moon. A slightly different angle, a slightly different speed, and the material would either have escaped into space or fallen back to Earth. The Moon would not exist. Ward and Brownlee assembled condition after condition. Plate tectonics, a magnetic field generated by a molten iron core, the right position in the galaxy far enough from dangerous stellar nurseries, the right chemical composition of the planetary crust. Each individually is perhaps not impossible elsewhere, but together, stacked, multiplied, the probability begins to collapse. Their conclusion was not that the universe is empty of life. Their conclusion was that the universe may be full of bacteria and nearly empty of anything more complex. Ward and Brownlee's hypothesis attracted significant pushback. Scientists, including James Casting at Penn State, argued that many of the proposed requirements were too strict, that life might be more adaptable than the rare Earth framework assumed, that moons and magnetic fields and stable tilts might not be as essential as claimed. Some critics pointed out that as exoplanet science advanced, we found planets in configurations we had not anticipated, and life on Earth proves remarkably creative in finding ways to persist in extreme environments. This debate is genuine and ongoing. Neither side has definitively resolved it. But what both sides agree on is this: even if the rare Earth hypothesis is only partially correct, even if only some of those conditions are truly necessary, the probability of finding complex, intelligent life drops dramatically compared to the optimistic estimates that launched SETI in the first place. The universe may contain many planets. The universe may contain many planets with microbial life. The number of planets that navigated every step of the complex life gauntlet may still be extraordinarily small. Set the rare Earth debate aside for a moment. Take a different angle entirely on the silence, not about whether life exists, but about whether we could possibly detect it even if it does. Humanity has been transmitting radio waves as a detectable signature into space for just over 100 years. That is, as we have established, a tiny fraction of cosmic time. But consider the inverse question: how long will we continue to use radio in a way that leaks into space? Already, in the decades since we began broadcasting, our radio footprint has been shrinking. Satellites replaced ground transmitters. Fiber optic cables replaced broadcast towers. Digital compression and precision targeting replaced wide-angle open transmission. A civilization monitoring Earth from 100 light-years away would have found our radio signature growing rapidly through the 20th century, and then beginning to fade, not because we stopped communicating, because we got better at it, and that pattern likely accelerates in any civilization that survives long enough. The technologies that produce detectable electromagnetic leakage into space are the primitive ones. As communication becomes more efficient, more directed, more sophisticated, it becomes less visible. A civilization 1,000 years more advanced than us might communicate using tightly focused laser pulses aimed directly at known target stars, invisible to anyone not standing exactly in the beam. They might use neutrino channels, particles that pass through entire planets without interacting with matter, carrying information that our instruments cannot currently detect at all. They might have developed forms of communication that require physics we have not yet discovered. The SETI Institute has acknowledged this explicitly. The traditional radio search is a search for one specific phase of technological development. If no civilization we find is in that exact phase at the same moment we are looking, the sky falls silent. Not because no one is transmitting, because the transmission is a frequency, a medium, a technology we have not yet learned to read. We are, in a certain sense, searching the cosmic library by looking only at one shelf. The shelf labelled 20th century radio technology, and concluding from its emptiness that the library holds no books. Now we reach the hypothesis that most scientists treat as the outermost edge of the conversation, the one that most researchers acknowledge as logically possible and almost immediately difficult to test, but which is too strange and too important to ignore. In 2001, British scientist and author Stephen Baxter published a formal paper in the Journal of the British Interplanetary Society titled The Planetarium Hypothesis. His argument was this: what we see when we look at the sky may not be what is actually there, a civilization advanced enough to harness the energy of an entire galaxy, what the Kardashev scale calls a Type 3 civilization, the theoretical maximum level of technological power, would have capabilities so far beyond ours that engineering our observable reality is not obviously impossible. Baxter proposed that such a civilization might create, around emerging civilizations like ours, what amounts to a perfectly rendered illusion, a virtual planetarium, a dome of false observations, engineered to show us an empty universe while the real universe, teeming with intelligence, continues beyond our perception. The name comes from the simplest human analogy. Stand inside a planetarium dome and look up. The stars projected on that ceiling look real. They are consistent. They respond correctly to the position of the observer. Nothing in the visible experience reveals that they are not the actual night sky. You would need instruments beyond your current capability, instruments that could probe the ceiling itself to discover the deception. Baxter's hypothesis was not written as science fiction. It was written as a serious, formally published scientific proposal. Scientists have taken it seriously enough to discuss its implications and testability in subsequent literature. And like the zoo hypothesis, it belongs in the catalogue of documented scientific possibilities. Not certainties, not even probabilities, but genuine logical resolutions to the paradox that cannot be dismissed simply because they are uncomfortable. Here is the most important thing to understand about all of these explanations. They are not competing with each other. The rare Earth hypothesis, if even partially true, means complex life is rarer than we assumed, but does not preclude other civilizations from choosing silence. The technological mismatch hypothesis means we may be searching in the wrong medium, but does not rule out a real scarcity of advanced life. The timing mismatch means temporal gaps could hide civilizations, but does not contradict the possibility that the universe genuinely produces few of them. Multiple explanations can be simultaneously true. The silence we observe could be the result of 3 or 4 or 5 independent factors, each reducing the probability of detection, each operating in parallel, each contributing to the same empty sky. A universe where complex life is genuinely rare, and some of those rare civilizations choose silence and use communication technologies we cannot detect and are separated from us by timing gaps no signal has yet bridged, would look exactly like what we observe. The silence is not one thing. It may be many things, layered over each other, reinforcing each other, conspiring to produce the same result from entirely different directions. This is what makes the paradox so resistant to resolution. Every time we imagine we have answered it, a new layer reveals itself. Every answer produces a deeper question. We have now moved through explanations rooted in behavior, in physics, in biology, in the structure of the universe itself. Each layer has pushed the mystery deeper rather than dissolving it. But all of these explanations have been about absence, about why we have not seen something. We have not yet turned the question around. What if we have been looking in the wrong places? What if the signatures of advanced civilizations are not in the radio spectrum at all? Not in the frequencies we scan, not in the signals we expect, but written in the light curves of distant stars and the infrared glow of entire solar systems, in objects that have already been observed and already been debated and already left scientists with a deeply unresolved question. Because there are things in this galaxy that have been seen, not signals, not transmissions, something potentially more significant and far stranger. The things that have been seen are not transmissions, They are not structured signals embedded in radio frequencies, waiting to be decoded. They are something older, something more physical, patterns in starlight, objects moving strangely through our solar system, the infrared glow of galaxies that scientists cannot fully explain with natural processes. They are the places where the universe seemed briefly to require an extraordinary answer, and in each case, scientists have had to wrestle seriously with a question they do not ask lightly. Could this be the work of something that built it? Before we can recognize the signature of an advanced civilization, we need a framework for thinking about what an advanced civilization would actually look like from the outside. What would it take, physically, to announce your presence to the cosmos, not through a radio message, but through the sheer scale of what you built? In 1964, Soviet astrophysicist Nikolai Kardashev published a 5-page paper that proposed the most enduring framework in the history of the search for extraterrestrial intelligence. He called it a classification scheme. We call it the Kardashev scale. Kardashev's idea was elegant in its simplicity. The most universal measure of a civilization's power is energy. Not culture, not biology, not intelligence in any abstract sense, but energy. How much of it can you harness? How much can you use? A civilization's answer to that question determines whether it is detectable from light years away. He proposed 3 levels. A Type 1 civilization has mastered its home planet. It captures and uses all the energy available to it from its local environment, including the full energy output falling on its world from its parent star. A Type 2 civilization has gone further, engineering structures to capture not just what falls on one planet, but the total energy output of their entire star, every watt, every photon directed and used. A Type 3 civilization controls the energy resources of an entire galaxy. These are not modest steps. A Type 2 civilization harnesses roughly 10 billion times more energy than a Type 1. A Type 3 civilization commands energy levels roughly 10 billion times beyond that. Each step is not a doubling. It is an exponential leap so vast that the distance between each level exceeds the distance between us and the most advanced technology we have ever produced. Where does humanity currently sit on this scale? Physicists, using the formula proposed by Carl Sagan to add finer gradation, estimate that we are currently at approximately 0.73. We have not yet reached the first rung. We have not yet fully harnessed the energy available from our own planet. We are, by this measure, a very early civilization in a cosmos that has had 13 billion years to produce advanced ones. If a civilization reached Type 2, physics tells us exactly what the evidence would look like. In 1960, the legendary physicist Freeman Dyson published a brief paper titled "Search for Artificial Stellar Sources of Infrared Radiation." His argument was precise and surprisingly simple. Any civilization that needed to capture the total energy output of its star would need to build structures around it. Not a solid shell, that is mechanically impossible, but a swarm of orbiting platforms, collectors and habitats, gradually enclosing more and more of the star's surface, capturing light that would otherwise radiate uselessly into space. Such a structure would not be visible in the way we normally see stars. A star wrapped in a Dyson swarm would look dimmer in visible light than its true brightness should suggest, and the energy it absorbed would eventually need to be released somewhere, as waste heat, as infrared radiation, glowing at temperatures much lower than the star itself. From across interstellar space, it would appear as a star with an anomalous infrared signature. More heat than expected, less visible light than the mass of the object should produce, a detectable fingerprint, a cosmic calling card, written not in radio waves but in the thermodynamics of energy transformation. Dyson pointed out that any civilization advanced enough to build such structures would be so energy-rich, and the structures so physically large that astronomers on distant planets should in principle be able to find them. He was not claiming they existed, He was saying, if they do, this is where to look. Dyson himself, it should be noted, later described the paper as something of a thought experiment. A little joke, he once said. Yet scientists took it seriously enough to search, and they searched in earnest. In 2015, astrophysicist Tabitha Boyajian and her team, working with data from NASA's Kepler Space Telescope and a network of citizen scientist volunteers through a project called Planet Hunters, flagged something in the data that stopped them. A star in the constellation Cygnus, catalogued as KIC 8462852, was dimming. Not in the way planets dim their stars. That kind of dimming is small, regular, predictable, and symmetrical. What Kepler recorded was irregular, asymmetric, sometimes a 1% dip in brightness, sometimes a dip of 22%. 22%. That is a staggering amount of obstruction. A Jupiter-sized planet, the largest kind of planet our solar system contains, passing in front of a sun-like star causes a dimming of roughly 1%. Whatever was blocking the light of this star was not a planet. It was something far larger. Something irregular in shape, or multiple somethings, moving in complex non-periodic patterns across the face of this star. The star, located roughly 1,470 light-years from Earth, meaning the light we see left it around 550 years before European explorers reached the Americas, earned a nickname, Tabby's Star, after Boyajian. And within months, one hypothesis had escaped the pages of scientific papers and entered headlines around the world. What if it was a Dyson swarm? Scientists were careful. The researchers involved consistently stressed that an alien megastructure was the least likely explanation on the table, but they also acknowledged that the data was genuinely strange and that no natural explanation immediately fit all the observations. The conversation was legitimate. The speculation was honest. Then Boyajian's own follow-up research began to close the door. As her team gathered more observations from multiple ground-based telescopes between 2016 and 2017, they measured something critical. The dimming was not the same at all wavelengths of light. Different colors of light were being blocked by different amounts. That single observation was decisive. A solid, opaque structure, like a constructed megaswarm, would block all wavelengths equally. Physics demands it, but dust absorbs and scatters different wavelengths differently. A non-opaque material would behave exactly as Tabby's star's dimming behaved. The science pointed, not dramatically but unmistakably, toward dust, irregular clouds, possibly orbiting debris from an ancient collision or disruption, creating the strange patterns Kepler had recorded. Scientists had considered an extraordinary possibility. They tested it seriously, and the universe answered with a more ordinary explanation. That is how science is supposed to work. But the case of Tabby's star is important, not because it confirmed anything alien. It did not, but because it revealed something about our search. We have the tools, at least in principle, to detect a Dyson swarm if one exists near enough to observe. And broad surveys of nearby stars and even entire galaxies for exactly this kind of anomalous infrared signature have been conducted. Researchers at Penn State, including astrophysicist Jason Wright, spent years scanning data from NASA's Wide Field Infrared Survey Explorer, scanning over 100 million cosmic objects. The GHAT survey, the Glimpsing Heat from Alien Technologies survey, found dozens of galaxies with possible infrared excesses. Every single one, on closer examination, appeared to have a natural explanation. No Dyson swarms confirmed, not one across hundreds of millions of objects examined. And then, in October 2017, something arrived. Astronomers at the Haleakala Observatory in Hawaii detected an object moving through our solar system on a trajectory that told them immediately, this did not come from here. Its path was hyperbolic. It entered our solar system from interstellar space, made a curving pass around the sun, and was leaving again. the first confirmed interstellar object ever observed passing through our cosmic neighborhood. Scientists named it Oumuamua, a Hawaiian word meaning roughly scout or messenger from afar. What followed was a genuine scientific controversy that has not been fully resolved. The object's shape was unusual. Initial measurements suggested it was elongated, with an aspect ratio unlike anything seen before among known asteroids or comets. That alone was remarkable. But what truly unsettled researchers was its trajectory after passing the Sun. As Oumuamua moved away, its acceleration could not be fully explained by gravity alone. Something was pushing it, faster than the gravitational forces of the Sun alone could account for. This non-gravitational acceleration is what triggered the debate. For a comet, such behavior is normal and expected. Comets release gas as they warm near a star, and that outgassing acts like a tiny rocket engine, nudging them off pure gravitational trajectories. But Oumuamua showed no visible signs of outgassing. No coma, no cloud of sublimating material surrounding it, no detectable dust. The most common natural explanation for non-gravitational acceleration did not visibly apply. Harvard astrophysicist Avi Loeb, founder of the Galileo project, published a paper in 2018, raising the possibility that Oumuamua might be a probe, a thin, flat object, perhaps a light sail, propelled by solar radiation pressure. The geometry required for that explanation demanded Oumuamua be extraordinarily thin relative to its surface area, a shape not previously observed in any known natural object. The majority of the scientific community pushed back. Multiple research teams at Yale University and elsewhere proposed alternative natural explanations. Among them, that Oumuamua might be a previously unknown type of object, perhaps a hydrogen-rich iceberg that sublimated invisibly as it warmed near the Sun. The debate continues. No consensus has been reached. Oumuamua is gone, long since departed our solar system, and unreachable by any spacecraft we could send. What it leaves behind is a question that neither side of the debate has fully closed. Not proof of intelligence, but a documented anomaly that required scientists to sit with genuine uncertainty about a cosmic object in ways that have rarely happened before. There is one more layer to this search for physical signatures that presses harder than any of the others. In the 1940s and 50s, mathematician John von Neumann developed a rigorous theory for machines that could reproduce themselves, mechanisms that, given raw materials, could build exact copies. The logic of self-replication is one of the most powerful forces in nature. Life itself is a form of self-replication, and a civilization advanced enough to build interstellar spacecraft could, in principle, build spacecraft that could build more of themselves upon arriving at new star systems, harvesting local materials, replicating, and dispersing outward exponentially. The mathematics of such probes is merciless in its implications. Even traveling at a fraction of 1% of the speed of light, far slower than the speed scientists consider plausible for advanced propulsion, a network of self-replicating probes launched by a single civilization could, by most estimates, fill the entire Milky Way within a few tens of millions of years. Mathematician Frank Tipler and others pointed out in the early 1980s that this means the absence of such probes in our solar system is itself an extraordinary observation. If even one civilization in the galaxy's 13.6 billion-year history had launched such probes, our solar system should almost certainly have been visited. We have mapped the inner solar system with remarkable precision. We have sent spacecraft to every major planet. We have tracked thousands of asteroids and comets. No artifact of non-human origin has been confirmed anywhere in our immediate cosmic neighborhood. Not one. But here is where the final, most unexpected possibility enters the picture. What if advanced civilizations do not expand outward at all? In 2008, astrophysicist and philosopher Milan Čirković at the Astronomical Observatory of Belgrade published a study examining two models of how a post-biological, technologically advanced civilization might behave. He called them the Empire State and the City State. The Empire State is the expansion model: spread outward, colonize stars, build megastructures, fill the galaxy. The City State is the opposite: optimize inward, build smaller, denser, more computationally efficient structures, concentrate intelligence into increasingly compact and efficient forms rather than spreading across light years of empty space. This idea connects to what some researchers call the transcension hypothesis, the possibility that the long-term trajectory of sufficiently advanced intelligence is not expansion into the physical universe, but expansion into inner complexity, towards smaller scales, toward the physics of dense information processing, quantum computing, the manipulation of matter at nanoscale, computation packed into a volume no larger than a planet or even a moon, a civilization that has transcended the need for physical expansion, would not build Dyson swarms that glow in the infrared. It would not launch von Neumann probes that flood the galaxy. It would not broadcast signals in all directions. It would shrink, optimize, become, from the outside, effectively invisible, not because it was hiding, but because the most efficient path forward led inward, not outward. And from our perspective, standing outside with our radio telescopes and infrared surveys and SETI algorithms, an inward-turning civilization would look exactly like no civilization at all. We have now searched with every instrument we have built. We have scanned the radio spectrum across hundreds of thousands of stars. We have measured the infrared glow of 100 million cosmic objects. We have tracked strange objects that pass through our solar system. We have searched for the waste heat of stars wrapped in engineering. We have found anomalies. We have investigated them carefully. We have watched them resolve, one by one, into natural explanations, or remain open questions that haunt the margins of the field. The universe has given us tantalizing hints, and then, in every case, it has offered another answer. This is the texture of the silence now. Not empty, not simple, not a single puzzle with a single solution, but a layered problem, with each layer making the next one harder. We still do not know if we are alone, and the question of what that means for us, not for ancient alien civilizations, but for this species, on this planet right now, is one that pulls the entire conversation in a very different direction. Because if the silence teaches us anything, it teaches us something about the weight of the decision we are living through. Before we can feel the weight of what the silence means, we need to reckon honestly with something that most conversations about the Fermi paradox quietly skip over. We have not actually searched the sky, not in any meaningful, complete sense, not even close. What we have done is something far more modest, and understanding exactly how modest it is changes everything about how seriously we should take the absence of an answer. In 2010, astronomer Jill Tarter, one of the most respected figures in the history of the search for extraterrestrial intelligence, offered what has become one of the most quoted analogies in all of science. Tarter had spent decades designing, refining, and leading some of the most ambitious listening projects humanity had ever attempted. She knew better than anyone how much effort had gone into the search, and she concluded that if you wanted to describe what we had actually covered, the honest image was this. We had taken a single drinking glass, filled it with water from the ocean, found no fish, and were considering whether to conclude that the ocean contained no life. 8 years later, astronomer Jason Wright at Penn State and his colleagues ran the mathematics more rigorously. They built a quantitative model of the search, not just physical space, but every dimension of the problem: frequencies monitored, signal strengths required, durations observed, directions sampled. They converted it all into comparable volumes, and they found that Tarter had been, if anything, slightly optimistic. Their calculation: all of humanity's collective SETI searches to date are equivalent to examining about 7,700 litres of seawater out of all the water in all of Earth's oceans combined. All of Earth's oceans contain approximately 1.3 trillion litres. We have searched the equivalent of a large hot tub. A hot tub. Not finding fish in a hot tub-sized sample does not tell you whether the ocean is full or empty. The absence of evidence in that sample is not evidence of absence across the whole. It is evidence only that our sample is extraordinarily small. But the challenge is not merely one of scale. The physics of electromagnetic radiation works against us in a fundamental way. Every signal broadcast into space, every radio wave, every laser pulse, every transmission of any kind, spreads outward in all directions from its source. As it expands, it covers an ever larger sphere of space. And because the total energy of the signal stays constant while the area it covers grows, the signal gets weaker with distance. Not linearly weaker, geometrically weaker. Every time you double the distance from the source, the signal strength falls to 1/4 of what it was. Double it again, and it falls to 1/4 again. Picture a bonfire on a flat plain at night. Standing next to it, the heat is overwhelming. A kilometre away, you can still feel warmth. 10 kilometres away, you might see a faint glow. 100 kilometres away, nothing. The fire has not changed. The energy has simply spread across too large an area for your sensors to detect it from that distance. This is what happens to any signal crossing interstellar space. A civilization broadcasting at the same power level we currently use for our strongest directional transmissions would be undetectable to our best current instruments at most distances within the galaxy. The physics of signal dilution over light years of empty space is merciless. Now consider what this means. Even if the galaxy is full of civilizations broadcasting right now, even if every one of them is producing transmissions roughly comparable to ours, the majority of those signals would simply vanish into noise before they reached us. Not because they were not sent, not because no civilization exists, but because the distances involved collapse signal strength below the threshold of any instrument we have ever built. This is the context in which the most ambitious search for extraterrestrial intelligence in human history must be understood. In July 2015, investor Yuri Milner and physicist Stephen Hawking stood before the assembled press in London and announced Breakthrough Listen, a $100 million 10-year program, the largest private investment in the search for extraterrestrial intelligence ever made. The program surveys 1 million of the nearest stars in our galaxy, scans the center of the Milky Way and the entire galactic plane, and listens for signals from the 100 nearest galaxies, 50 times more sensitive than any previous dedicated SETI program, covering 10 times more of the sky, operating 100 times faster, using the most powerful radio telescopes on 6 continents, including South Africa's Meerkat array, which produces more data per second than most scientific instruments ever designed. Artificial intelligence algorithms comb through the resulting data, petabytes of it, a volume so large that no human team could ever manually inspect it, looking for the statistical signatures of non-natural signals. Machine learning systems trained specifically to distinguish the patterns of artificial transmission from the endless natural radio noise of the cosmos. And yet, as of today, no confirmed technosignature, not one verified signal of non-natural, non-terrestrial origin has survived the scrutiny of peer review and independent confirmation. This does not mean Breakthrough Listen has failed. In the context of the cosmic haystack problem, it means precisely the opposite. Breakthrough Listen has dramatically extended our reach and revealed, more clearly than any previous effort, how far we still have to go. It is, as astrophysicist Andrew Siemian of the UC Berkeley SETI Research Center described it, the Apollo program of the search for extraterrestrial intelligence, a revolutionary leap in capability. And still, in the context of what the universe actually requires us to search, it is barely the beginning. Even setting aside distance and scale, the search faces a dimension of the problem that is difficult to overstate. We do not know what frequency to listen on. Radio is not a natural medium of communication. Radio waves are one small band within the full electromagnetic spectrum, the range of wavelengths that carry energy. That spectrum extends from the extremely low frequencies used by submarines to communicate through water, all the way to gamma rays capable of penetrating solid rock. Between those extremes lies an enormous range of possible frequencies, and we have no way of knowing which ones an advanced civilization might choose to use. SETI researchers have focused heavily on a range near the frequency of neutral hydrogen, the most abundant element in the universe, which naturally emits at a specific frequency that any civilization with basic radio astronomy would recognize. The reasoning is sound. A universal frequency, known to all technologically capable minds, provides a natural Schelling point, a meeting place that requires no coordination to identify. But this logic only holds if the transmitting civilization is broadcasting with our detection capabilities in mind, at roughly our current level of technological development. A civilization 10,000 years ahead of us might have abandoned broadcast radio entirely. As we have noted, our own radio footprint is already shrinking as our technology improves. A civilization far older might use communication methods that our current science cannot even describe clearly. Tightly focused laser pulses aimed with precision at specific targets. Neutrino beams, particles that pass through the entire mass of the Earth with almost no interaction, carrying information at intensities we currently cannot measure. Quantum entanglement-based protocols operating in ways that look like nothing our instruments can detect. The universe of possible communication channels is not just large. For a civilization far enough ahead of us, it is fundamentally unknowable from our current position. We are, in a real sense, searching the equivalent of one radio station, while billions of other channels exist on the dial. And beneath all of this lies the deepest statistical question of the search. Even if the universe is full of life, even if every habitable planet teems with organisms, as the early emergence of life on Earth might suggest is possible, the transition from microbial life to technological intelligence may be extraordinarily rare, not impossible, not ruled out, but genuinely profoundly unlikely to happen more than once across vast stretches of cosmic space and time. We have one confirmed example of intelligent technological life, us, and we arrived after 4.5 billion years of evolutionary history on a planet that required every one of the conditions described in the rare Earth framework. Every mass extinction that wiped out competitors and cleared ecological space for new complexity. Every chance merger of cells and chromosomes that produced the eukaryotic architecture. Every coincidence of climate, continental geometry, and atmospheric chemistry that built the conditions for large brains to be advantageous. Even if simple life is common, even if microbial ecosystems exist on countless worlds across this galaxy, the specific, staggeringly improbable chain of events required to produce a species that builds radio telescopes and points them at the sky may have happened only rarely. Perhaps only here. In that case, the universe is not silent because intelligence is hiding, not because the signals are undetectable, not because civilizations come and go without overlapping our brief window of observation. The universe is silent simply because minds capable of speaking into it are genuinely rare events in cosmic history. But hold one final possibility in mind before we leave this layer of the problem. Several researchers, including cognitive scientist and evolutionary biologist Robin Hanson and the team at the Future of Humanity Institute at Oxford, have explored a scenario in which the silence is real and self-imposed, in a way that has nothing to do with fear or strategy. Advanced civilizations, at some point in their development, may transition away from physical space entirely, not in any mystical sense, in a deeply physical one. A civilization sophisticated enough to construct dense computational substrates, matrices of information processing far beyond anything we can currently build, might find that the richest, most interesting, most rewarding universe available to them is not the cold, sparse, three-dimensional cosmos they were born into. It is the inner universe of computation, of simulated reality, of experience and intelligence compressed into a volume no larger than a small moon, operating at densities of thought and information that dwarf anything possible in the physical world. A civilization that chose this path, inward rather than outward, would produce no megastructures, no radio signals, no von Neumann probes, no infrared excess around its home star. From the outside, it would simply vanish, present one day, gone the next, not because it died, because it found a richer existence in a direction our instruments cannot point, and a universe full of such civilizations, each one brilliant beyond our imagining, each one turned inward toward its own depth, would look, from our position, exactly like an empty sky. The silence does not prove we are alone. The mathematics of the search does not permit that conclusion. A hot tub of ocean water proves nothing about fish. The quiet of our radio receivers proves nothing about the fullness or emptiness of the galaxy. But here is what the silence does tell us, with clarity that no argument can fully dissolve. We are here, now, in this precise, brief window of cosmic time. We are the only species we know of that has built the instruments to ask these questions, developed the mathematics to calculate the odds, and found ourselves staring into a universe that has not yet answered back. Whatever the silence means, whether it is the product of distance, timing, technology, rarity, or the inward turn of minds older than we can imagine, it carries a message about us, about what we are, about what this moment represents, about the decisions that now fall to a civilization that has no elder to consult and no precedent to follow. The silence is not just a puzzle about them, it is a mirror held up to us. A mirror does not tell you what is out there, a mirror tells you what is here, and every argument we have examined, every layer of silence, every explanation for the absence of signals, every possibility from the great filter to the timing mismatch, has ultimately been reflecting something back at us, not about alien civilizations, about this one, about what it means that we are, as far as we can determine, the only species in the observable cosmos currently asking these questions, about what that means for the next century of decisions we are about to make. Because the silence is not a passive observation. The silence is an instruction. Every interpretation of the great silence resolves into one of two broad possibilities, and the gap between them, in terms of what they mean for us, may be the largest gap that has ever existed between two answers to the same question. The first possibility: we are rare. Not just statistically unlikely, but genuinely profoundly exceptional in a cosmos that produces life frequently, but almost never produces minds capable of building civilizations. The great filter is behind us. We pass through it, through the improbable emergence of the eukaryotic cell, through the unlikely development of multicellular complexity, through the catastrophic series of evolutionary near misses and lucky coincidences that eventually produced a species capable of looking outward. If this is true, the universe is not crowded with peers. We may be the first technological civilization in a substantial volume of cosmic space, and perhaps one of very few that have ever existed. The second possibility, the filter, is ahead of us. Life and intelligence arise with some regularity across the galaxy, but almost none of it survives to the stage of spreading across stars. Something, perhaps many things, perhaps different things for different civilizations, ends the story, and every civilization that has reached our level, roughly the level of splitting atoms and building computers and standing on the edge of being able to travel to other worlds, has faced that same convergence of forces that we are beginning to face now. Both possibilities carry weight. Neither is comforting in the simple sense. But the second one carries something closer to urgency. Take the first scenario seriously for a moment. If the great filter is behind us, if the silence reflects genuine cosmic rarity rather than imminent failure, then what we hold in our hands is almost incomprehensibly valuable. Not just the accumulated achievements of human history, the potential future. Picture a civilization that survives this century, that navigates its own technological adolescence without destroying itself, that spreads eventually to other worlds, carrying with it the capacity for curiosity, art, science, love, memory, and meaning. That seeds the galaxy not with conquest, but with the kind of complexity that took 4 billion years of blind biological luck to produce here. In a universe where such minds are rare, where we may be among the first, that future is not just valuable to us. In some sense, it may be among the most significant developments in the 13.8 billion year history of the observable cosmos. The universe, through us, gains the capacity to understand itself, to look outward and name what it sees, to feel wonder about its own existence. If we are rare, the stakes of every decision we make about our collective survival are not merely civilizational, they are cosmic. Now take the second scenario just as seriously. Oxford philosopher Toby Ord spent years studying the probability of civilizational catastrophe. His 2020 book, The Precipice, remains one of the most rigorous assessments ever published of the risks facing humanity in the coming century. His conclusions are not alarmist speculation. They are careful, documented, peer-reviewed estimates. Ord's estimate: there is roughly a 1 in 6 chance that humanity suffers an existential catastrophe within the next 100 years. 1 in 6. That is the same odds as a single roll of a standard die, landing on any one number. Not remote, not theoretical, a probability that any rational person assessing a situation would find serious cause for concern. And what composes that risk? Natural hazards, asteroid impacts, supervolcanic eruptions, the processes that have ended civilizations on geological timescales, account for only about 1 chance in 10,000 per century. Negligible. What dominates the risk profile are the technologies that intelligent civilizations almost inevitably develop: nuclear weapons, engineered biological agents, and the emerging question of misaligned artificial intelligence. These are not freak accidents. These are the predictable consequences of the very intellectual capacity that makes a civilization detectable in the first place. Here is the disturbing logic connecting the silence to our situation. Any civilization that develops nuclear technology, or biotechnology, or advanced AI arrives at precisely the crossroads we are standing at now. A moment where the tools of creation and the tools of destruction are the same tools, where the same intelligence that launches telescopes toward the stars could, through negligence or malice or catastrophic miscalculation, end the story before the next chapter begins. If that is the filter, if the development of transformative technology is also the moment that ends most civilizations, then the silence of the galaxy is not a mystery without a message. The message is, almost no one gets through this part, and that means we are trying to be the exception. The silence confronts us not just with the abstract question of our survival, but with a very concrete ethical question about what we do next. Since humanity first built powerful radio transmitters, we have been, without intending it, audible to any sufficiently advanced civilization within about 100 light-years of Earth. Not loudly, our leakage radiation is relatively faint, but audible in principle. For over a century, the electromagnetic envelope of our civilization has been expanding outward at the speed of light, announcing that something technologically active exists here. But some scientists argue we should do far more than passively leak. They argue we should deliberately broadcast powerful, structured, intentional messages aimed at nearby stars. This practice has a name: messaging to extraterrestrial intelligence, or METI. And in 2015, when an organization called METI International was founded specifically to do this, the debate that had simmered within the scientific community for decades erupted into something approaching a genuine schism. At one pole, the late physicist Stephen Hawking. In 2015, at the very announcement of the Breakthrough Listen project, Hawking said clearly what he thought of deliberately announcing our presence. His reasoning was blunt. Meeting an advanced civilization could be like Native Americans encountering Columbus, he said. That didn't turn out so well. A civilization billions of years ahead of us, he argued, might find us no more significant than we find bacteria. The asymmetry in power is the problem. We cannot know the intentions of a civilization so far ahead of us, and the cost of being wrong is everything. At the other pole, scientists including Douglas Vakoch and Alexander Zaitsev have argued that staying silent is itself a choice with consequences. The knowledge and perspective of an advanced civilization, if it is benign, which is equally unknown, might be precisely what allows us to navigate the existential risks we face. And those who counter that it is too late to hide point out something difficult to dismiss. Any civilization advanced enough to travel interstellar distances would already be able to detect the biosignatures of Earth's microbial life, which have been altering our atmosphere for 2 billion years. Our existence is not secret. The scientific community's response in 2015 was not a ban on METI. It was a call, published by dozens of researchers at the American Association for the Advancement of Science, for global consultation before any deliberate high-power transmission. The argument was simple. This is not a decision that belongs to a small group of scientists or to any single nation. A transmission aimed at the stars speaks for every human being alive, and all human beings who will ever live. That debate has not been resolved. The tension between reaching outward and moving carefully remains exactly where it was when Hawking and Vakoch stood on opposite sides of it, and it will likely remain there until the question of who speaks for Earth has a better answer than it currently does. Whatever the silence means, one lesson is written into every layer of it, without ambiguity. We are not the final word. The universe built the eukaryotic cell before it built us. The universe assembled stars and planets and habitable zones for billions of years before the sun ignited. The universe has been conducting its experiments for a span of time that makes human history look like a breath held for a fraction of a second at the end of a very long day. If intelligence has arisen elsewhere, even rarely, it almost certainly arose earlier, perhaps much earlier. And if such intelligences exist or have existed, they looked back at a cosmos that was not built to accommodate their preferences, and they faced the same fundamental choice we face: adapt or disappear. There is a particular kind of humility that the silence imposes on us, not the humility of smallness. We have known for centuries that we are small, but the humility of contingency, of recognizing that we are not inevitable, that nothing about the cosmos guarantees our continuation, that the extraordinary cascade of accidents that produced us does not commit the universe to protecting us. And inside that humility, paradoxically, lives something strengthening. Because a species that understands its own contingency, that genuinely grasps the fragility of the thread it stands on, can also understand the importance of taking extraordinary care with that thread. The silence does not counsel despair. The silence counsels attention, rigor, foresight, the building of institutions and technologies and systems of cooperation worthy of a civilization that has understood the stakes. Philosopher Toby Ord notes that humanity currently spends less than 1/1000% of global economic output on reducing existential risk. Less than 1/1000%. On the single category of problem that, if it goes wrong, eliminates all future value the universe might derive from our existence. The silence, read carefully, suggests this is an extraordinary mismatch between the scale of the risk and the scale of our response. But the silence is not only a warning, it is also an invitation. Every great search in the history of science began with a question that appeared, to some, to be either unanswerable or unimportant. The search for exoplanets seemed unlikely to succeed until Kepler proved otherwise. The search for the origin of life seemed beyond science until chemistry and geology began to find their first footholds. The search for gravitational waves was considered almost impossibly ambitious until the LIGO detectors heard the collision of two black holes more than 1 billion light-years away, a sound that no human ear could perceive, but that our instruments translated into a moment of profound confirmation. The search for extraterrestrial intelligence is still in its earliest stages. The instruments are improving, the algorithms are becoming more sophisticated, the frequency ranges we monitor are expanding. The concept of technosignatures has grown to encompass not just radio signals, but atmospheric chemistry, infrared anomalies, and eventually the direct imaging of exoplanets by missions like the proposed Habitable Worlds Observatory. We are not standing still, and the simple act of searching, of taking the question seriously, of funding the instruments, of training the people who will use them, is itself meaningful. Not because success is guaranteed, but because a civilization that stops asking whether it is alone has, in some sense, already lost part of what makes it worth preserving. The silence in this sense is not the end of the story. The silence is what makes the next page worth turning. We began this journey with a simple observation. The universe is extraordinarily large, extraordinarily old, and by every calculation we know how to make, full of conditions that should have produced intelligence many times over. Yet the sky is quiet. We have walked through the physics and the biology and the history and the ethics of that quiet. We have looked at what might explain it. We have looked at what it means if each of those explanations is true. And now we stand at the place where all of those threads converge, not in a solution, not in a clean resolution, but in something quieter and more permanent. A single question holding everything we have explored in suspension. Are we alone or simply unheard? And which answer would change us more? Are we alone or simply unheard? Those two questions do not have the same answer, and they do not carry the same weight. Being alone implies something about the universe, about what it produces, about how common minds are, about whether the cosmos builds complexity or merely permits it in rare, accidental pockets. Being unheard implies something about us, about the limits of our instruments, the brevity of our window, the parochialism of our assumptions about what an intelligent civilization should look like from the outside. Both possibilities rest on the same observation: a quiet sky, but the quiet sky, held up to the light of everything we have explored, turns out to be anything but simple. We began this journey with an observation that felt obvious. The universe is vast. The numbers are overwhelming. By every calculation we have developed, from the Drake equation to the latest exoplanet surveys from Kepler and its successors, the cosmos should be teeming with intelligence, and yet the sky is silent. Not silent the way a blank wall is silent. Silent the way a room goes quiet the moment you walk in. The particular kind of silence that carries a question inside it. A silence that tells you something is happening that you do not yet understand. What we have found, moving through the layers of this problem, is that the silence does not yield to any single explanation. Not because the universe is withholding an answer, but because the answer is genuinely uncertain, and has been uncertain from the beginning. The absence of confirmed signals does not prove that no civilizations exist. The absence of confirmed megastructures does not prove that no advanced engineering has ever occurred anywhere in this galaxy. The absence of any confirmed contact does not tell us that the universe is, in fact, empty. What the silence tells us, carefully and precisely, is that we have not yet heard. And those are very different things. Here is the thing about the search for extraterrestrial intelligence that most accounts leave unexamined. The search has never only been about finding them. The search has always been in equal measure about understanding ourselves. When Frank Drake sat down with a small group of scientists in Greenbank in November of 1961 and wrote 7 symbols on a chalkboard, he was not simply calculating probabilities. He was doing something more philosophically audacious. He was insisting that the question of whether we are alone in the cosmos is a scientific question, not a theological one, not a philosophical one, not a matter of faith or intuition or cultural mythology, a question that can be approached with instruments and mathematics and careful, honest reasoning. That insistence changed something fundamental about how humanity saw itself. Before the search, before Drake, before SETI, before Kepler, before the era of confirmed exoplanets, we had only the vastness of the sky and our imaginations. After the search, we had data, we had constraints, we had the honest acknowledgement of how much we do not know, mapped with a precision that pure speculation could never achieve. The hot tub of ocean water metaphor is not a failure, it is a measurement. It tells us where we are in the search and where we have yet to go. What the silence has taught us about our expectations is profound. We expected the universe to reveal itself on our timescale, through our preferred medium, on the frequencies our instruments were already designed to receive. We expected that any intelligence in the cosmos would, at some point, look in our direction and decide that we were worth addressing. We expected, in short, that we were central enough to the story that the story would eventually come to us. The universe has not confirmed that expectation, but the universe has also not denied it. Sit with one fact for a moment. You exist in a universe that is 13.8 billion years old. The atoms in your body were forged in the cores of stars that lived and died before the sun was born. The carbon in your cells was assembled over billions of years of biological iteration, from chemistry so unlikely that we still cannot fully replicate it in a laboratory. The neural architecture that allows you to comprehend language, to feel wonder, to read meaning into the pattern of stars, that architecture took 4 billion years of blind evolutionary process to build, from a starting point so primitive that it would not be visible to the naked eye even under a bright light. You are not the product of a design. You are the product of an extraordinary accumulation of improbable events, each building on the last, each surviving the cosmic equivalent of a roll of the dice, with odds that should have produced nothing. And yet, here you are. The universe, in at least one place, assembled matter into the capacity for self-reflection, into the ability to construct mathematics and music and memory, into the specific, remarkable ability to look outward at the cosmos that built it and feel something in response. Call it wonder, call it curiosity, call it the strange loop of awareness that allows a collection of atoms to ask where the other collections of atoms are. Whether we are alone in that capacity or not, whether this has happened elsewhere, once or 1,000,000 times, the fact that it happened here at all is extraordinary enough to demand a certain quality of attention. The absence of evidence is not evidence of absence. This principle, widely cited and sometimes misunderstood, carries real weight in the context of the Great Silence. We have searched a hot tub's worth of cosmic ocean. We have monitored a fraction of the possible frequencies for a fraction of the possible durations, aimed at a fraction of the possible targets. We have built our search around the assumption that other civilizations broadcast in ways we can currently detect, using technologies broadly similar to our own, at roughly our current stage of development. Every single one of those assumptions could be wrong. At the same time, and this is the crucial balance, the absence of evidence is also not nothing. It is a constraint, a genuinely powerful one. It tells us that if advanced civilizations exist in large numbers in our galaxy, they have, for whatever combination of reasons, not made themselves unmistakably obvious at the scales and frequencies we have been monitoring. That is a real statement about the universe, even if it leaves a vast range of possibilities open. The puzzle of the silence is not solved, but it is no longer just a feeling. It is a precisely described scientific problem, with a growing body of methodology for investigating it, a community of rigorous researchers dedicated to its study, and an expanding set of instruments and techniques that will, in the decades ahead, push our sample size from a hot tub to something considerably larger. The absence of an answer does not mean the question was wrong to ask. There is a particular kind of loneliness that the silence can produce if you let it, the image of humanity as the only voice in an enormous, indifferent cosmos, speaking into a void that will never answer. But that is only one way to read what we have found. Another reading goes like this. We have been looking for peers, for mirrors, for intelligences that developed along broadly similar paths to ours, that face broadly similar problems, that can offer us the confirmation we apparently crave that complexity and consciousness are natural products of cosmic evolution. We have been looking for a sense that we are not anomalies, that what happened here was not accidental, or at least not uniquely so. The silence may be telling us that the universe does not produce peers easily, that the path from chemistry to conversation is so narrow and so difficult that it rarely gets travelled even when all the physical conditions are favourable, that what we have here, this fleeting, improbable, magnificent architecture of awareness, is among the rarest things the cosmos constructs. And if that is true, then the silence is not evidence of cosmic indifference. The silence is evidence of cosmic scarcity, of a universe that can, under the right circumstances in the right places across billions of years, produce something this complex and this strange. But that does not do so often. The silence, read that way, does not diminish us. The silence asks us to take ourselves and each other, and this moment, more seriously. We have not resolved the Fermi paradox. That honesty matters. Science does not always offer closure. Some questions, when approached with complete rigor and complete honesty, reveal themselves to be genuinely open, not from lack of intelligence or effort, but because the universe has not yet given us the data needed to close them. The Fermi paradox is one of those questions. The great filter is one of those questions. Both will remain open until one of several things happens. Until we develop instruments sensitive enough to detect the signatures we might be missing, until we find life somewhere else, microbial, complex or technological, until we fail to find it after exhaustive search of a far larger haystack, which would itself be a statement of enormous significance, or until some signal arrives that we did not anticipate in a form we did not predict from a direction we were not monitoring. Any of those outcomes would be among the most consequential discoveries in the history of our species. All we can do in the meantime is keep looking, keep improving the tools, keep refining the search, keep asking the question with the rigor it deserves, and keep being honest about what we do not know. Step outside on a clear night and look up. Every point of light you can see is a star. Most of those stars almost certainly have planets. Many of those planets sit in habitable zones where liquid water could persist. Some of those worlds may harbour life that has never been named, never been observed, never intersected in any way with the brief flicker of awareness that is human civilization. Or none of them do. The sky holds both possibilities simultaneously. We cannot yet tell which. What we can say is that the question itself, the fact that we are standing here under this same sky that has witnessed the entirety of cosmic history, asking whether we are its only observers, is an achievement of staggering improbability. The universe did not have to produce a species capable of this question. The laws of physics do not require it. The history of the cosmos does not demand it. And yet here the question is, here we are. The silence is not an answer. The silence is an invitation to build better instruments, to think more carefully about our assumptions, to take seriously the possibility that we are standing at an extraordinary moment in the history of complexity, a moment when a small blue world in one unremarkable arm of one spiral galaxy among 2 trillion has developed the capacity to reach outward into the cosmos and ask, with honesty and rigor, whether it is alone. Whatever the answer turns out to be, the asking of the question is itself a form of participation in something ancient and vast and ongoing. We are the universe asking whether it is alone. We have travelled a long way together tonight, through the size of the cosmos and the loneliness of the search, through the logic of the great filter and the strangeness of Oumuamua, through the ethics of broadcasting and the mathematics of a hot tub of ocean water. I want to sit with you for just a moment before we part, not to explain anything more, just to acknowledge what it means that you were curious enough to ask these questions in the first place. That curiosity, that refusal to accept the sky as mere decoration, is the same thing that put a radio telescope on a hillside in West Virginia in 1960 and pointed it at the stars. It is the same thing that makes this question worth asking at all. The silence may never fully resolve, but the fact that we are listening for an answer is, perhaps, the most human thing about us. We started with a room gone quiet, a silence that does not feel like emptiness, that feels like something that was happening before you arrived, and whatever it was, it stopped. That particular quality of silence that carries a question inside it. Now, after everything we have examined, that room feels different. The silence is not the absence of sound. The silence is the presence of a question that human beings have been asking, with increasing precision and increasing honesty, for the entirety of our short scientific history. A question that has no confirmed answer. A question that may not have one for decades or centuries. A question that may, one day, resolve in a single transmission, a single anomaly in the light of a distant star, a single piece of evidence that changes every conversation humanity has ever had about its place in the cosmos. Until that day, if that day comes, the silence stands, not as an answer, as the most profound open question our species has ever had the courage to ask. Are we alone? We do not know. And that understanding that we do not know, but that we are asking and looking and listening with everything we have, may be everything that matters. The universe has been here for 13.8 billion years. For nearly all of that time, as far as we know, nothing in it asked a single question. And then, in one small corner of one ordinary galaxy, something changed. Matter arranged itself, slowly and improbably, into the capacity for wonder, into the ability to look outward at the darkness and feel the weight of not knowing, into a species that builds telescopes not just to see, but to search, to reach, to refuse to accept silence as an answer. You did that tonight. You sat with one of the hardest questions the cosmos has ever produced, and you did not look away. That is not a small thing. If this journey stayed with you, if it left you sitting quietly for a moment, looking at the ceiling, feeling the strange dignity of not knowing, please consider subscribing. It means more than the number suggests. It means there is one more person willing to ask the uncomfortable questions. And the next time you step outside and look up at the night sky, remember this. A universe that produces a mind capable of asking whether it is alone has already done something extraordinary. You are part of that extraordinary thing. Thank you for being here.